You ever notice how time can just slip away? You get caught up in something and boom, an hour's gone.
Yeah, definitely.
Well, Einstein took that kind of feeling that time isn't always constant and, well, he kind of blew up physics with it. Welcome to the deep dive, everybody. You've said over some really interesting stuff on Einstein's theory of relativity, and today we're going to try to break it down.
Sounds good.
See what makes it tick,
Yeah.
figure out why this theory still shakes things up, even after all these years. We'll cover both his special and general theories of relativity. We'll be looking at space, time, momentum, energy, all that fun stuff, all based on this summary you shared. Einstein's Relativity, Space, Time, and Motion. Great title.
Yeah, really gets to the heart of it.
So let's just jump right in. Special relativity, where do we even begin?
Well, the amazing thing is it all starts with two ideas that seem pretty basic at first. First one, the laws of physics are the same everywhere, for everything moving at a constant speed.
Okay, I think I follow. Like, it doesn't matter if I'm here in the studio or floating in space. Physics works the same.
Yeah, exactly. Imagine you're in a spaceship, just cruising along smoothly. Any experiment you do inside, it'll give you the same result as if you did it right here on Earth. That smooth, constant movement where you're not speeding up or slowing down, that's what physicists call an inertial frame. And Einstein's big idea is that there's no special preferred inertial frame. They're all equal.
So, like, the universe doesn't care if you're standing still or zooming along. The basic rules are the same. Gotcha. But that second idea, that's where things get a bit wibbly-wobbly, right? Something about the speed of light.
You got it. This is where it gets really interesting. Einstein said that the speed of light in a vacuum, that's empty space, is always the same for everyone, no matter how the light source is moving or how you, the observer, are moving.
Hold on. That doesn't sound right.
Yeah.
Like, if I throw a ball forward while I'm on a moving train, it'll seem faster to someone standing on the platform, right?
With everyday objects, yes. But light's different. It doesn't follow those normal rules. There was this famous experiment, the Michelson-Morley experiment. They tried to measure how Earth's movement affected the speed of light. And guess what? No change at all.
Huh. So light's got a speed limit then?
You could say that. It's a cosmic speed limit. We call it c, and nothing with mass can go faster ever.
All right, so these two seemingly simple ideas, they lead to some seriously weird results. Like, the thing that always messes with my head is this relativity of simultaneity. You're saying that two things happening at the same time for me might not be simultaneous for someone else moving differently.
Exactly. It's like this: imagine a train zooming by and lightning strikes at both ends at the exact same time for someone standing in the middle of the tracks. But for a passenger sitting in the middle of the train, they're moving towards one lightning strike and away from the other. Since light travels at a constant speed, they'll see the strike they're moving towards first. So for them, those two strikes weren't simultaneous at all.
So what now is different for them?
In a way, yes. The idea of now becomes relative to how you're moving. And that leads us to one of the most famous consequences: time dilation. Time itself can stretch or shrink depending on your speed.
Okay, now that is just trippy. So how does that work?
Well, let's say an event takes a certain amount of time to happen. We call that the proper time, written as delta t0. Now, someone moving relative to that event will measure a different time, delta t. The faster they're moving, the longer that delta t will be. There's a special factor called the Lorentz factor, gamma, that tells us how much time is distorted. It's calculated using the speed of the observer and the speed of light. The formula is gamma equals 1 divided by the square root of 1 minus u squared divided by c squared.
Ooh, math. But I think I get the gist. So the faster you go, the slower time seems to pass for you compared to someone who's stationary.
That's the idea. And it's not just theoretical. We've seen this in experiments. For example, certain particles, muons, they decay very quickly. But when they're moving at super high speeds, they last way longer than they should because their time is stretched out from our perspective.
Whoa. So if we could travel near the speed of light, we'd age slower than everyone back on Earth.
Theoretically, yes.
That's mind-blowing. And wait, it's not just time that's affected, is it? Length changes too.
You're thinking of length contraction. Exactly right. If you measure an object at rest, that's its proper length, written as L0. But if it's moving relative to you, you'll measure it as shorter along the direction it's moving. This is calculated using the Lorentz factor again, L equals L0 divided by gamma. And importantly, this shortening only happens in the direction of motion. Its height and width stay the same.
So, like, a spaceship zooming past would look squished, shorter but not thinner.
Precisely. And again, this isn't just an illusion, it's a real physical effect of how space and time are connected.
So how do we keep track of all these changes? Time dilating, length contracting. It's getting hard to wrap my head around it all.
Well, that's where the Lorentz transformations come in. They're a set of equations that let us translate between different frames of reference. Like, if you know where and when something happens in one frame, you can use these equations to find out where and when it happens in another frame that's moving relative to the first.
Okay, so these equations are like a universal translator for space and time.
You could say that. They show us how space and time are intertwined into this single entity called space-time, where neither has an absolute meaning on its own. And you know what's fascinating? At slow speeds, like what we experience daily, these equations simplify and become almost the same as the classical physics equations we used before Einstein. That's why we don't see these relativistic effects in our everyday lives.
So it's like relativity is always there, but it only becomes really noticeable at super high speeds. Okay, I think I'm starting to get the hang of this. But what about speed itself? How do we measure that when things are zipping around near the speed of light?
Good question. That's where the Lorentz velocity transformation comes in. It tells us how to calculate the speed of an object in one frame if we know its speed in another frame that's moving relative to it. And this equation is really important because it shows us, again, that nothing can travel faster than light, no matter how the frames are moving relative to each other. It's like that cosmic speed limit is baked into the very fabric of the universe.
And finally, before we move on, there's this thing called the relativistic Doppler effect, right? Like with sound, how a siren sounds higher pitched when it's coming towards you and lower when it's moving away.
Exactly. It happens with light, too. If a light source is moving towards you, its frequency shifts towards the blue end of the spectrum, what we call blue shift. If it's moving away, it shifts towards the red end, which is red shift. It's how we can tell if stars and galaxies are moving towards or away from us.
Okay, so special relativity has totally flipped our ideas about space and time. But Einstein didn't stop there. He then applied these concepts to momentum and energy. So tell me, what happens to those concepts when we're dealing with these super high speeds? Did Newton's laws just go out the window?
Not exactly. Newton's laws are still very useful at everyday speeds, but they need some tweaking for objects moving near the speed of light. Take momentum, for example. In classical physics, momentum is simply mass times velocity. But in relativity, it's a bit more complex. We still use mass and velocity, but we multiply them by that Lorentz factor, gamma, again. So the faster something goes, the bigger its momentum becomes, and it actually approaches infinity as the speed gets closer and closer to the speed of light.
So like even a tiny object would have a huge momentum if it was moving near the speed of light.
Yeah, exactly. And this ties back to that cosmic speed limit. Because momentum gets infinitely large as you approach the speed of light, it would take an infinite amount of energy to actually reach it. So nothing with mass can ever get there.
It's like the universe has this built-in safety mechanism. But what about force? Does Newton's second law, F equals ma, still hold true in this relativistic world?
Well, it still works, but we have to think of it in terms of the change in relativistic momentum. Force becomes the rate at which that relativistic momentum changes. And the relationship between force and acceleration gets a bit more complicated. It depends on whether the force is pushing the object in the same direction it's already moving or perpendicular to its motion. But the key takeaway is that as an object gets closer to the speed of light, it becomes harder and harder to accelerate it further, no matter how much force you apply.
Okay, I see. It's like trying to push a shopping cart that gets heavier the faster it goes.
Yeah.
What about kinetic energy? That's the energy of motion, right? How does that change?
Kinetic energy gets a relativistic makeover, too. The classic formula, 1/2 mv squared, still works at low speeds, but it's not the whole picture at high speeds. Einstein came up with a new formula that takes into account the energy contained within the mass of the object itself. And what's amazing is, at low speeds, this relativistic formula simplifies down to the classic formula. It's like Newton's equation was hiding a deeper truth all along.
It's beautiful how these concepts all connect. And speaking of connections, that brings us to perhaps the most famous equation in all of physics, E equals mc squared.
Yeah, that's the one. And it comes from the idea that even when an object is completely at rest, it still possesses a certain amount of energy just because it has mass. We call this rest energy. And the equation E equals mc squared tells us exactly how much energy is locked up in that mass.
So mass and energy are basically interchangeable.
That's the profound implication of this equation. They're two sides of the same coin. And this leads to the idea that mass can be converted into energy and vice versa. And that's what powers things like nuclear reactions, the sun, nuclear power plants. It's all about converting a tiny bit of mass into a tremendous amount of energy.
That's pretty heavy stuff. But if I understand correctly, these relativistic effects, they mostly come into play at incredibly high speeds, near the speed of light. So does that mean Newtonian physics is wrong? Do we just throw it out the window?
No, not at all. It's more like Newtonian physics is a special case, a very good approximation of reality at low speeds. The key principle here is called the correspondence principle. It basically says that any new theory in physics has to agree with the old theories in the areas where those old theories have been proven to work. So, for everyday objects moving at everyday speeds, Newtonian physics works perfectly well. We don't need relativity to build bridges or design cars.
So it's not about one being right and the other wrong. It's more like relativity is a bigger picture that encompasses those classical laws.
All right, that makes sense. So, special relativity gave us this whole new understanding of motion, space, and time. But then Einstein took things even further with his general theory of relativity. Then we're talking about acceleration and gravity. This is where things get really wild, right?
You could say that. General relativity takes the principles of special relativity and expands them to include any frame of reference, even ones that are accelerating, and it completely revolutionizes our understanding of gravity.
Okay, I'm all ears. Tell me more about this gravity revolution.
Well, the key idea is what we call the principle of equivalence. It says that there's no way to tell the difference between being in a gravitational field and being in an accelerating frame of reference. Imagine you're in an elevator and it starts accelerating upwards really fast. You feel pressed down to the floor, right? That feeling is exactly the same as if you were standing on the surface of a planet with a stronger gravitational pull. So the force that keeps us grounded on Earth is the same feeling as being pushed back in your seat when a car accelerates.
Exactly. And from this idea, Einstein developed the incredible concept that gravity isn't actually a force at all. It's a curvature of space-time caused by mass and energy.
Hold on. Space-time is curving.
Yeah, picture it like this. Imagine a bowling ball on a trampoline. The ball creates a dip, a curvature in the trampoline's surface. Now roll a marble across the trampoline. It won't travel in a straight line. It'll curve towards the bowling ball because of that dip. That's kind of like how gravity works. Massive objects like stars and planets warp space-time around them, and other objects, even light, follow those curved paths.
So the Earth is orbiting the Sun not because of some invisible force pulling it in, but because the Sun has warped the space around it, and the Earth is just following that curve.
That's the idea. It's a completely different way of thinking about gravity, and it's been confirmed by a lot of observations and experiments. For instance, the way light bends around massive objects, like during a solar eclipse, that's exactly what general relativity predicted.
So it's not just some fancy theory. It's actually how the universe works. That's incredible. And this theory, it's not just for understanding far-off stars and galaxies, right? Does it affect us here on Earth too?
It absolutely does. General relativity is crucial for things like GPS, the global positioning system, the thing that tells your phone where you are. Those GPS satellites are up in space, moving fast and experiencing weaker gravity than us down here. That means their clocks run slightly differently than clocks on Earth.
Because of time dilation.
Exactly, both from special and general relativity. And if we didn't take those tiny differences into account, GPS wouldn't be accurate at all. It'd be off by miles every day.
So even something as simple as using our phones for directions depends on Einstein's crazy theories.
Pretty much. It's all connected.
Wow, we've covered a lot of ground today. From the mind-bending consequences of special relativity to the revolution in our understanding of gravity with general relativity. Einstein's work has truly transformed how we see the universe. It's amazing how a few seemingly simple ideas can lead to such profound insights.
It really is a testament to the power of human curiosity and the elegance of the universe itself.
It makes you wonder, what other mysteries are out there waiting to be uncovered? What other seemingly unshakable assumptions we have about reality might be overturned by future discoveries? And to think, all of this amazing stuff came from just one chapter on Einstein's relativity. Well, hopefully, this deep dive has given you a good grasp on this incredible theory. There's a lot to unpack, but it's definitely worth the effort.